Well, see, in the last lecture, I have given you this homework. So let's see. It's very simple. This is a cyclic process starting from here to here, A to B, B to C, C to A. So this work is equal to, we can write area enclosed. Area enclosed. And area enclosed is equal to, we can write half into delta P into delta V, right? Delta P is this and delta V is this. So this is 1 by 2 into delta P is 1 minus 0.5. This is 0.5 and delta V is 10 liter ATM. So this is 5. So 2.5 into 101.2 joules. 1 liter ATM is equal to 101.2 joules. So if you solve this, so you will get what? 101.2 multiplied by 2.5. So this is 253 joules, right? And see, this is what? Clockwise. So since this is clockwise movement, so the work is negative. So you can see delta W is equal to minus 253 joules. This is answer. And if you want, you can calculate from here to here, from here to here. Then some, it might be possible that some more data is required, like temperature is required. Although if pressure is there at this point, volume is there, so quantity is required, 1 mole or 2 mole gas, and nature of gas, CPCV. So in that way, step by step also you can calculate. But this is the simplest way to calculate the work if nothing is given. So simply you can take the area enclosed by the figure and check the clockwise or counterclockwise. So this is clockwise, so negative, right? So now let's do one more practice, one more question. So so that you becomes comfortable during, for this thermodynamics first law questions based on the thermodynamics first law. See, 2 moles of an ideal gas at 1 atm and 27 degrees Celsius undergoes the following process. Step 1, the heat absorbed at constant volume till the pressure is doubled, right? Isothermal reversible expansion till the pressure is 0.8 atm and adiabatic compression till the initial stage reached, right? So these are the 3 different steps given in the question, and find the delta E, delta W, delta Q, even delta H can be also asked for each step as well as for the total cycle. CV is given, and also plot P versus V for the cycle, right? So see, step 1, first we see the step 1. Step 1, right? See, volume constant, V constant, V constant, right? So now gas, ideal gas, 1 atm, 27 degrees Celsius. This we move to ideal gas, V constant, isochoric, and ideal gas, and till the pressure is doubled. So 2 atm, right? And we don't know how much temperature is there because it is not given in the question. So T2. So this is the I mean change in state as per this given condition. So P1 is equal to 1 atm, P2 is equal to 2 atm. This is known quantity. V1 we don't know, but we know that V2 is equal to V1, right? T1 is equal to 27 plus 273. So this is 300 Kelvin. 300 Kelvin. And T2 we don't know, right? What is T2? And number of moles we know 2 moles, right? So P1 is known, P2 is known, T1 and T2 and this moles constant. So we can, volume is constant, moles is constant, so we can relate pressure with temperature. So what is the formula? P1 by T1 is equal to P2 by T2. P1 is 1 atm by 300 Kelvin is equal to 2 atm and T2. ATM cancel. So T2 is equal to 600 Kelvin, right? Volume is constant. So what is work here? Volume is constant. dV is equal to 0. So delta W is equal to 0. And once delta W is equal to 0, you can write delta E is equal to delta Q as per the thermodynamics first law. First law means the heat absorbed basically in this step, that is equal to the change in internal energy, right? Heat absorbed at this stage is basically the change in internal energy. So you can write here NCV delta T. So this is equal to 2 moles. CV is equal to, I think it is given, 40 joules per mole per Kelvin, 40 joules per mole per Kelvin, and delta T is 200 Kelvin. Kelvin, moles. So this is 16,000 joules. So you can write 16.0 kilojoule, right? 16.0. Oh, 300. Sorry. 300. So this is 24. 24 kilojoule, right? So this is heat change and change in internal energy both for this step. Clear to everybody? Okay. So this is the heat change or change and change in internal energy. energy, right? Now come to the step 2. Step 2. So in step 2, what is the this state? So ideal gas 2 atm 600 Kelvin to some other state, ideal gas, and this time what is given? Isothermal reversible expansion till the pressure is 0.8 atm. So 0.8 atm and 600 Kelvin isothermal, 600 Kelvin, right? So this is the change, and moles, n is equal to 2 moles is still, n is equal to 2 moles, the process is isothermal. So this time, since process is isothermal, then delta E is equal to 0, because there is no change in the intermolecular forces, or there is no cleavage of any kind of bond. If there is a cleavage of intermolecular forces, if there is a cleavage of bond, then definitely under isothermal condition delta E is not equal to 0. So you can write here no dissociation or association, dissociation or association of intermolecular forces, intermolecular forces or atomic or bonding intermolecular forces or interatomic forces, interatomic forces. So basically this is the cause of delta E is equal to 0 if temperature is constant. Why this delta E is 0? This is the explanation for this. If there is a change in the intermolecular forces or interatomic forces, then even temperature is constant, there is some change in internal energy. So due to this, what we can write here, delta Q is equal to minus of delta W, right? And this is a reversible process, so we can write here minus P gas dV, right? 1 to 2. So this is, I am writing here minus minus plus 2.303 nRT log P1 by P2. Direct formula I am using. All of you are knowing this formula. So 2.303 into 2 moles into 8.314 joules per mole per degree Kelvin, and temperature is 600 Kelvin, 600 Kelvin, and log P1 is 2 atm by 0.8 atm, right? Log 2 by 0.8. So when you solve this, so you will get the answer. So this is calculation of this will give you 9.143 kilojoule, right? So this is step 2. You have calculated delta Q, delta W, and delta E. Now come to the step 3. Step 3. So step 3, ideal gas 0.8 atm and 600 Kelvin, and now this will move adiabatic ideal gas or initial state. So in the initial state, what is the pressure? 1 atm. And what is the temperature? 300 Kelvin. So this is initial state. Initial state, right? So see, adiabatic means delta Q is equal to 0. Delta Q is equal to 0. So delta E is equal to delta W, or we can write delta W is equal to NCV delta T. So to calculate this work, you want delta T, you just require delta T CV, and both the things are given, and moles. So 2 moles CV is 40 joules per Kelvin per mole, and delta T 300 minus 600. This is the final temperature, and this is the initial. Initial means for step 3, this is initial and this is final, right? So Kelvin. So Kelvin, Kelvin cancel, moles, joules per mole. Mole cancel. So you will get minus 24,000 joules. So minus 24 kilojoule, right? So you have calculated delta Q, delta W, and delta E for this step. Now see, delta for the complete cycle, delta E is equal to delta E1 plus delta E2 plus delta E3. So see, this is delta E1 is 24 kilojoule plus delta E2 is 0. Oh, excuse me. And delta E3 is minus 24 kilojoule. So this is equal to 0. Right? Now see, delta W is equal to delta W1 plus delta W2 plus delta W3. This is equal to 0 plus in the step 2, what is the work? Basically work is this 9.143 kilojoule plus, in this case work is minus 24 kilojoule. So this is equal to 24 minus 14.85 kilojoule, and delta Q is equal to delta Q1 plus delta Q2 plus delta Q3. So this is equal to, in the first case, what is delta Q? Delta Q is 24 kilojoule. 24 kilojoule plus, what is delta Q2? Here 9.143, 143 plus 0, right? So this is minus basically, and so this is equal to what? 4.85 kilojoule, right? So if you see, if you want, you can cross check this. Delta E is equal to W, and this is equal to 0, right? So see, this is the complete, right, calculation of heat change, work, and internal energy change in the complete cycle as well as for each step, right? Hopefully now it is clear to all of you. Now see, some expressions for specific heat. See, we have two types of specific heat at constant pressure and constant volume. So, if any one depends on temperature, then second one also accordingly you can find the value of that. So, more familiar term is CP. So, I am talking about CP here. Although if nothing is given in your question, then you have to assume CP and CV are independent of temperature, right? But CP, this depends on temperature in fact, and empirical equation is given for this dependency of CP with temperature. A plus BT plus CT square plus DT cube and so on. What this is one expression through which we can evaluate the magnitude of CP at different temperature if this constant A, B, C are given. One more relation is there. CP is equal to A plus BT, A dash plus B dash T, right? Plus C dash by T square, right? This is equation 2. Both are empirical equations determined experimentally. So here the important factor is A, B, C, and A dash, B dash, C dash are the constants, and depends on the nature of the substance. As CP and CV also depends on the nature of the gas, nature of the substance. So if you have this value A, B, C, or A dash, B dash, C dash, then you can very easily determine the magnitude of CP at I mean given temperature. See example for this. Example, determine the CP for water at 300 Kelvin, water gaseous at 300 Kelvin, and at 1000 Kelvin, and at 1000 Kelvin, right? A is equal to 30.36 joules per Kelvin per mole. B is equal to 9.615 into 10 power minus 3 joules per mole per Kelvin, joules per mole per Kelvin to -2, and C is 12 into 10 power -7 joules per mole per Kelvin to power -3. So see, this is a very simple question. Now, which equation you are going to use? Equation 1 or equation 2? Obviously, A, B and C, value of A, B and C is given, so we use this equation 1. So Cp is equal to A 30.36 joules per Kelvin per mole plus B 9.615 into 10 power -3 into T at 300 Kelvin. This is 300 Kelvin into joules per mole per Kelvin to -2 plus 12 into 10 power -7 joules per mole per Kelvin to the power 3 into 300 square, Ct square, 300 into 300 Kelvin square, right? Now you can solve this, so you will have this value 33.35 joules per Kelvin per mole, right? This is at 300 Kelvin, right? Now at 1000 Kelvin, see Cp, this is equal to 30.36 joules per Kelvin per mole plus 9.615 into 10 power -3 into 1000 Kelvin into joules per mole per Kelvin to the power -2 plus 12 into 10 power -7 joules per mole per Kelvin to the power -3 into 1000 into 1000 Kelvin square, right? So if you solve this, so you will have value 41.17, 41.17 joules per Kelvin per mole. So see, at 300 Kelvin you have this Cp value, at 1000 Kelvin you have this Cp value. So what you are getting, increase or decrease? Increase, right? So Cp increases with rising temperature, and this rise, increase in Cp is mainly due to the contribution of vibrational energy in the Cp and Cv, right? So this is the dependency of Cp and Cv on temperature, right? One more example we can do here. Example, calculate the change in enthalpy. Calculate the change in enthalpy, change in delta H, right, of 1 mole of CO2 if it is heated from 300 Kelvin to 1000 Kelvin, right? And given A is equal to 26.86 joules per Kelvin per mole, B is equal to 6.966 into 10 power -3 joules per mole per Kelvin and C is equal to 8.243. 8 point, yes, 8.243 into 10 to the power minus 7 joules per mole per Kelvin minus 3, right? So change in enthalpy, basically, so all of you are knowing that this equation delta H is equal to NCP delta T, right? NCP dt. NCP dt. So for 1 mole, this is the basic equation. For N is equal to 1 mole, we can write here delta H is equal to Cp dt, right? And this T1 to T2, right? So we can write here 1 to 2. So delta H2 minus delta H1, this is equal to T1 to T2 Cp dt. So this is the equation 2. So by simplifying this equation, and we know Cp is equal to A plus Bt plus Ct square. This is equation 3. So if we put here and integrate this, then we can calculate. So what is the T1 to T2 A plus Bt plus Ct square dt, right? So this is equal to A T2 minus T1 plus 1 by 2 B T2 square minus T1 square plus 1 by 3 C T2 cube minus T1 cube, right? Now you can put the value and get the answer. So A is equal to 26.86 thousand minus what, 300, 1000 minus 300, yes, 300 units are as usual, plus 1 by 2 into B 6.966 into 10 power minus 3 into 10,000 square, so 336 10 power 6 minus 9 into 10 to the power 4, right? 9 into 10 power minus 4 plus 1 by 3 into C 8.243 into 10 power minus 7 1000 cube minus 300 cube 27 10 power 6. So if you solve this, you will have the value 22.24, 22.24, right, kilojoules per mole. So this is the change in enthalpy of any reaction when you change the temperature from 300 Kelvin to 1000 Kelvin. But this you can calculate only when this is given what CP relation constant value A, B and C is given. Sometimes this equation also represented like this: delta H2 minus delta H1. This is equal to Cp for 1 mole, right? And T2 minus T1. T2 minus T1, right? So this equation, this also gives the variation. So here when you are assuming Cp is independent of temperature, right? Cp is independent of temperature. So this is also, and this equation is known as Kirchhoff's equation. Kirchhoff's equation. But here Cp is independent of, Cp is assumed to be independent of temperature. Right? So Cp, if Cp is independent of temperature, then this, right? And sometimes, suppose that this question is given, equation is given: A gas plus 2B2 gas gives AB4 gas. Suppose that this question is given, and so for this you can write delta reaction Cp per mole. This is equal to sigma of Cp of product minus sigma of Cp of reactant, right? So you can take this equation delta. So this equation delta H is equal to, or delta H2 minus delta H1 is equal to delta reaction Cp per mole into T. So this equation also you can use to calculate delta H. So at constant temperature, due to the change in the nature of the matter, Cp will change. Here Cp is not depends on temperature. Here Cp changes with the change in the matter. Here reactant is A, reactant is B2, and after reaction this is completely finished, and AB4 you are getting. So AB4 have different atomicity, different structure, so different Cp. So if this type of question is given, means chemical reaction is given, temperature constant is given, then also you can change, you can calculate the delta H, and that will come from the change in the Cp, and it is not equal to 0 although temperature is constant, right? So these are the important equations. Kirchhoff's equation, delta H dependency on temperature by assuming Cp is independent. This is temperature constant, but also delta H is not equal to 0, but this time this is not equal to 0 due to change in the nature of the matter. So this reaction, this equation is also popular, and you will find this type of question in your thermochemistry problems, right? So this is all about this Cp and its dependency on temperature. See, in this question, I have forgotten one thing that it is given. Also, plot P versus V for the cycle, right? So, PV plot I should mention here. So, P V PV. So, suppose that initial state is this 1 atm and 300 Kelvin, right? And 2 mole gas is given. Okay. So, uh, what they have given first case, mm, pressure is doubled. So, pressure is doubled and volume is constant. So, this 2 atm and 600 Kelvin. 600 Kelvin. So this is the first path basically. This is the step 1. Now isothermally we are moving to the reversible and isothermal process, and we are moving somehow this pressure point 8. So pressure point 8, this is the pressure coordinate. So pressure point 8 is somewhere here, point 8 atm, right? And isothermal means temperature 600 Kelvin. So isothermal path like this, right? So this is the step 2. And then adiabatic, from here to here, this is adiabatic. I have taken so a long distance here. Okay, now it is clear. So this is adiabatic step 3. So like this, the plot of this PV plot for this all three changes. This is isothermal, this is adiabatic, and this is isochoric, right? Now see, sometimes transformation of different curves may be asked to you in the question. So suppose that I am taking first isobaric heating. Suppose that isobaric baric heating. So isobaric heating given if for any gas. So we can explain this on the different curves. Isobaric heating means pressure is constant. So if we take this P versus V plot, so this is like this. Isobaric, this is initial state A and this is final state B, like this. So when you heat, temperature will rise. So volume is also rise. So isobaric heating is represented on the PV curve like this. Suppose that instead of PV curve, if examiner has asked this VT curve, so now it is clear that isobaric condition is there. So whenever you take V versus T, Kelvin, so Charles law, remember Charles law, and you will get this type of curve. So this is initial state A and this is final state B. So this type of movement you will get. And if P versus T plot is given, I mean given or asked, so P versus T, P versus T, so it is like this, and this is A and this is B. See, at A point your pressure is more and temperature is what, less. So here if you see here in I mean this is this graph, this plot, how I have decided that this point is A and this point is B, not this point is A and this point is B. Here it is also clear that at this point temperature is low at this point. Here also the temperature is low at this point. Ta is less than Tb. Ta is less than Tb, right? Ta is less than Tb because P and V product is less here compared to this. So here Ta is less than Tb. So here also Ta is less than Tb. So here Ta is less than Tb. So you can justify by I mean transforming PV into PT or VT plot if isobaric heating is given. Similarly, if isochoric heating is given, isochoric heating is given, choric heating is given. So in isochoric heating, if P versus V, isochoric means this type of curve we may get, and heating means this is A point, so this is B point. So heating means isochoric heating means pressure is increased. So at this point PB, I mean you can say TB is more than TA because at this point pressure is more. Similarly, if PT plot is asked for this, volume constant, so similar graph as VT graph. PT A, this is B. Similarly, if VT graph is asked, so here V and here T, constant volume. So in this way you can justify, right? So these are the different, plots and interconversion of one type of plot into other type of plot you can see.